I think you're already familiar with Netflix originals. But contrary to what you may believe, House of Cards was not the first Netflix original. It was in fact Lilyhammer, a crime comedy series, back in 2012. Originals are shows and movies that are created and produced by Netflix Studios. This is enabled by the Netflix Studio platform, which provides the platform and the tooling for bringing these creations to our users across the globe. Hello everyone, my name is Anoop Panicker, and I'm a member of the Content Middleware Infrastructure team at Netflix. Our team builds, maintains, and most importantly, evolves the Studio platform in a way that is completely seamless and transparent to our end users. So how do we do this? In this session today, we will be looking at how these systems were evolved to support new requirements with no impact to end users. As you already know, at Netflix, we are all about good storytelling. We'll set the context for where we are set, and then we will dive into some of the impetus that drove some of these evolutions. We will then dive into a couple of case studies where we will look at the why, the what, and the how for why these migrations were performed. Then we will wrap up with some of the patterns that we've observed and the learnings that we've gathered during these migrations. We hope that at the end of this session, we have been able to touch on some of the principles and patterns that apply widely and in many cases can be abstracted and highlighted to build robust, flexible, and resilient architectures. Netflix launched its first original in 2012 and then gradually expanded its content slate over the next couple of years. The Studio platform was created and developed in lockstep. This platform validated and fortified the business processes that were required for bringing a content creation from an idea to member joy to our users across the globe. Around 2016, Netflix launched globally and is currently available in more than 190 countries. The content that is created globally is made available to a global audience by our Netflix streaming service. The tooling for the studio and the infrastructure needed to evolve to support the growing demand and keep up with the operational and technological advancements. The show truly had to go on. The Studio platform has since undergone several iterations over the years as the scale and reliability requirements have gone up. As you can see in the infographic, the growth of the Netflix Studio was truly exponential, and currently, more than 50% of the content on Netflix are Netflix originals. The Netflix Studio platform empowers the pitch-to-play lifecycle of every piece of content while being scalable, effective, and cost-efficient. Now let's look at some of the catalysts that sparked the need for these migrations. The transition from the MVP phase to a global-wide adoption was expedited by the exponential growth of the content slate, as we saw earlier. This led to several operational challenges in maintaining the platform, some of which stemmed from the scaling limitations of individual components. We also observed data inconsistency issues as a business process moved across its various stages of its lifecycle through domains. The reliability of the platform was being stress tested, but it was paramount to uphold customer trust. To put it into monetary terms, even a few seconds of downtime could lead to millions of dollars lost in production value. So what does performing infrastructure evolution on a global scale system really feel like? Some of the noteworthy constraints: absolutely no downtime is tolerable. The global availability of the system cannot be compromised. Even a slight degradation or partial failure can severely impact business functions. I think this image does a fairly good job of providing an analogy. For this session, we will be focusing on Conductor, which is a key infrastructure component in the Netflix Studio platform. Conductor is part of the Netflix OSS suite of tools and was open sourced in 2017. It is a workflow orchestration platform that enables users to bring their own workflows and tasks to weave together business processes that span across domains. Usage of Conductor is prevalent across the Studio platform, primarily because it abstracts away the operational burden from individual teams while providing granular observability and self-recovery in failure scenarios. If you would like to learn more about Netflix Conductor, please visit the GitHub page and read the documentation. This is a 30,000 feet view of the Netflix Conductor architecture from when we started in 2017. For the purposes of this talk, we will focus on the data plane. The Conductor data plane primarily used Dynamite as the primary persistence layer. DynoQueues, which is a queuing recipe built on top of Dynamite, provided the queuing abstraction required for scheduling tasks and orchestrating workflows. Elasticsearch provided the indexing layer, which enabled searchability across dimensions and task payloads. For the first case study, we will look at how we migrated away from Dynamite to Cassandra for our primary persistence. At the same time, we also introduced AWS S3 as an augmented storage layer. Now let's look at some of the triggers for why this migration was necessary. Dynamite is an in-memory data store built on top of Redis. This means that the scalability of the database itself is bounded by the scalability of the instance that it is hosted on. This limitation was partly introduced because of an inefficient sharding strategy that was chosen when the database was first provisioned. The topology will also constrain the number of database connections that are available, which severely limited the conductor's horizontal scalability. Furthermore, a distributed data model was chosen for the primary persistence, which meant that in the absence of transactional guarantees and a lack of anti-entropy mechanism provided by Dynamite itself, the shards that became inconsistent remained inconsistent till the node was replaced. A lack of use case vetting or usage modeling led to really large payloads being stored into our primary persistence. This forced us to work with our users and adopt aggressive archival techniques to ensure that Dynamite nodes always had enough free memory to serve growing traffic. Now let's look at that last point about the storage issues in more detail. The payloads that were being stored as part of workflows and tasks were being accessed by auxiliary processes, not necessarily part of the workflows themselves. Such requests resulted in increased latencies and CPU usage on Dynamite, which meant that the Tomcat worker pools that were part of Conductor were getting exhausted, thereby increasing the rejection rate. As more such workflows were being executed, the availability and reliability of the platform was being compromised. Self-recovery mechanisms were built into Conductor, but they were unable to keep up, and the resiliency of the system was taking a hit. We charted a strategy to address these issues. We launched several user campaigns to understand the usage of the system and to educate our users about the data flow. We leaned on to AWS S3 for providing the external storage capability. We also adopted a tiered storage model, which meant that beyond a soft barrier, workflows and tasks would store their data in AWS S3. And beyond a hard barrier, we would outright reject the payload and fail the execution. Now that we had a better understanding of the data and the usage, we set out to design the persistence layer based on access patterns and the critical path. Leaning into the NoSQL ideology, we chose a denormalized data model for storing the data in Cassandra, such that an entire workflow's execution would be stored in a single partition. Additionally, we also built in a logical sharding option to allow this model to be scalable such that the application could choose when to shard a particular workflow across multiple partitions. Since Conductor is an open source project, we use open source DataStax drivers to interface with the database. However, we wrote this implementation in a pluggable manner such that we were able to use our own internal custom drivers to interact with Cassandra when we deployed it internally. For the migration itself, we chose something that we refer to as the switch pattern. The strategy, like its eponym, works just like flipping a switch. Based on the characteristics of the usage and the workflow executions themselves, we determined that no data migration was necessary. All the currently running workflows were allowed to complete in Dynamite, where all new workflow executions would be started in Cassandra. For a very small percentage of workflows, approximately 0.3%, an opportunistic read before write approach was used, but this was a trade-off that we were willing to take in lieu of migrating data. Now let's look at how the migration was performed. This diagram illustrates the before and after of the migration phase. As seen in figure A, all the CRUD operations for the database were routed directly through to Dynamite by our DAO layer before the migration. As you can see in figure B, during the migration, we introduced a migration layer which expanded on each of these operations in detail and routed them accordingly. All the create operations were proxied directly through to Cassandra. The read operations were proxied to Dynamite first and then to Cassandra, depending on the response. In certain cases, reads could be parallelized between Dynamite and Cassandra. For update operations, we would proxy to Dynamite first and then to Cassandra, depending on the response. For deletes, we were able to parallelize them across both data stores. Here again, We use a switch pattern to determine which database to access first, depending on how far along we are in the migration process. This strategy allowed us to make this migration completely seamless and transparent to our users with no downtime or impact. I will now hand over the reins to my colleague Kishore, who will take us through to the end of the session.
Thank you, Anoop. Hello, everyone. My name is Kishore, and I will continue the story to the next case study and then to the ending. Anoop and I have been working together for more than 5 years, and we have built several systems together. We're glad to share some of our learnings here today. In this case study, I want to talk about how we migrated our queue service from DynaQueues to Timestone. DynaQueues is a queuing recipe built on top of Dynamite. Timestone is a distributed priority queue system built by our team for Conductor and similar use cases. After our first migration, this is what we ended up with. Our primary store is migrated to Cassandra and S3 while we are still relying on DynaQueues. Queues is an important component of Conductor, and Conductor uses queues in many ways. But of most importance is the worker lifecycle coordination. And thus, the reliability of the queuing system is very important for Conductor. So why do we have to do this migration? As I mentioned earlier, DynaQueues is a queuing recipe built on top of Dynamite, which means it inherits most of the limitations of Dynamite, as Anoop talked earlier. In particular, one of the challenges we have faced are the writes in DynaQueues are round-robin, while the reads are availability zone local. This wouldn't work well for some of our use cases, meaning the messages in a particular queue shard in a specific AZ are not being able to poll until a Conductor node in that AZ polls for that message. In addition, for the lack of anti-entropy, as Anoop talked earlier, we would have to frequently intervene manually. So when we start out this migration, we have set up certain goals. The first one is that the migration should be completely transparent to the users. And then the data in DynaQueues shouldn't be impacted. No new data should be added into the DynaQueues. The existing data, when touched, should be ported to Timestone. And then finally, we want to drain off DynaQueues completely as soon as possible and then remove the dependency. So here is how we do this migration. We have added a migration layer leveraging the Roman writing pattern to orchestrate between Timestone and DynaQueues. This allowed us to keep the API backwards compatible with no changes whatsoever. Here is how it works. On NQueues, the new messages will go to Timestone. Whereas on DQueues, we go to DynaQueues first and then to Timestone. It's the same for removal of message as well. You might be wondering what happens to the messages that are just NQ'd to Timestone. For example, consider a case where a certain queue might have 100,000 messages already in DynaQueues, but then we are NQing new messages into Timestone. And then we are not pulling the messages that are just NQ'd into Timestone. Counter this particular edge case, we used a separate deployment of migration layer where we are pulling only from Timestone using a switch pattern. This allowed us to pull simultaneously from Timestone and DynaQueues while still having the migration layer enabled. In the end, we were able to drain the DynaQueues in about a day, and then we decommissioned it a week later. So when we started this migration, we have devised an extensive test setup to verify our migrations end to end. Our test setup consists of 3 steps: before, during, and after. So before the migration, we simulate near production traffic using load drivers. And then we get some baseline metrics and ensure the existing setup works normally, meaning the health checks, API operations, service level agreements, etc. are honored. And then we enable the migration layer while still keeping Timestone disabled. This allows us to verify the health of Timestone and rule out other hiccups. That's how we leverage switch pattern to control between Timestone and DynaQueues again. And then during the migration, we correlate the metrics we collect with the metrics we collected earlier to rule out any abnormalities or service degradations. We also ensure that the messages are still being able to poll from both the DynaQueues and Timestone while no new messages are being pushed to DynaQueues. And then after the migration, we verify the messages in DynaQueues are drained completely and then we remove the migration layer. And finally, we end by verifying the health of timestone and then other metrics being correlated with the first version of the migration. We have run this setup tens of times to hash out all the hiccups and increase our confidence in migration tremendously. After this migration, this is where we got to. You might have noticed there are a few other migrations in this picture that we haven't talked about. For example, migration of the Elasticsearch layer through Kafka. We want to share some of the patterns we have learned from migrating evolving systems over the years. Note that these patterns are not exclusive and you might see a lot of overlap. We might be using a handful of them in each of the migrations. To begin, a switch pattern, as Anoop talked about during Cassandra migration, is simply a flip between path A versus path B. Whereas a knob allows for more fine-grained control of the percentage of the data you want to flow between the migrating services. For example, you can control and say, I want 25% of the data to flow to Cassandra versus Dynamite. And then a gate uses database semantics to gate the flow of control. This enables granular selective routing. For example, we used a gate pattern to direct a particular workflow execution to an older execution engine versus a new engine. Roman writing is very useful when navigating both parts of the system simultaneously. Queue migration is a very good example of this. A migration layer acting as a control plane provides required knobs and metrics while allowing you to combine with other patterns mentioned earlier. This has been super helpful and we have relied on this pattern heavily for several of our migrations. And then a testing framework with load drivers to simulate production loads, and then a before-after during setups, or maybe automation to run this setup multiple times, have greatly improved our confidence in migrations. And finally, a red-black deployment testing, where you would have coexisting code deployments with one of the knobs from above layers, helps verifying the connectivity and then rule out data model correctness and service level degradations, etc. And to end, we would like to share some of the learnings. The first one is keep checking the health of your dependent systems and include that in your test plan. When we are running into issues with DynaQueues, we realized we had to include that in our system design. And then we went on to build a workflow repair service that goes and fixes the workflows that are inconsistent state automatically. And then continue to monitor your usage patterns and correlate them with your dependency patterns. This allows you to measure and stay in track with your dependencies while not outgrowing them. We are fortunate to have extensive tooling at Netflix to help test and verify our evolutions over the time. Chaos Monkey, Canaries, etc. are some of the tools that we have heavily leveraged. Build guardrails to ensure that the contracts are honored but not abused. For example, during the data store migration, we have set up payload limits on the workflow to avoid abuse from users by storing large amounts of data in the workflows. Avoid split brain situations as much as possible, where you'd have to maintain both the older and newer versions simultaneously. And then you'd have to deal with the conflict resolution and other associated problems because of that. And then for testing, consider evolving your test scope as the scope of your application increases. Have a repeatable setup that evolves over the time. And then consider automating your test setups similar to how we have done with the before, during, and after migration setup to improve your confidence in overall system evolution. Finally, plan ahead on how you want to evolve and formulate a plan of action to avoid any surprises. Conductor 4.0 migration, which we have done very recently, is super silent given the scope of the migration. And that brings us to the end of this session. But I don't think this will be our last migration. We hope you have learned a few things from our experience, and thank you for joining us.